About 4.6 billion years ago, our solar system was a swirling cloud of gas and dust, known as the solar nebula. This vast and chaotic cloud was the birthplace of everything we see in our solar system today, from the smallest asteroid to the largest planet. This nebula, mostly composed of hydrogen and helium, was the leftover material from the formation of our Sun. These elements, the simplest and most abundant in the universe, were the building blocks of the solar system. Gravity, the force that governs the motion of celestial bodies, acted upon this cloud, pulling it inward. This gravitational collapse was the first step in the transformation of the nebula into a structured solar system. As the nebula collapsed, it began to spin faster, much like a figure skater pulling their arms in. This increase in rotational speed caused the cloud to flatten into a disk, a shape that would dictate the future arrangement of the solar system. This spinning motion caused the cloud to flatten into a disk, known as the protoplanetary disk. Within this disk, the seeds of planets, moons, and other celestial bodies began to form. At the center of this disk, the Sun ignited, blasting out light and heat. This young star, now a blazing beacon in the center of the disk, provided the energy necessary for the next stages of planetary formation. The remaining dust and gas in the disk continued to swirl around the newborn star. These remnants of the nebula were the raw materials from which planets would eventually emerge. Over millions of years, particles in the disk collided and stuck together, gradually growing larger. These collisions were not random. They were governed by the laws of physics, which dictated how particles would interact and combine. These clumps attracted more and more particles, eventually forming planetesimals, the building blocks of planets. These small celestial bodies, through a process of accretion, grew larger and more complex over time. One of these planetesimals, located at just the right distance from the Sun, would eventually become Earth. This location, within the so-called habitable zone, was crucial for the development of conditions suitable for life. Early Earth was a hot, molten ball of rock, constantly bombarded by asteroids and comets. These impacts delivered not only energy, but also essential elements and compounds that would later contribute to the development of life. The energy from these impacts, combined with the heat from radioactive decay within Earth's core, kept the planet in a molten state. This intense heat caused the differentiation of materials within the planet, setting the stage for the formation of its core, mantle, and crust. Over time, the bombardment slowed and Earth began to cool. This cooling process allowed the surface to solidify, forming the first crust, while volcanic activity continued to shape the landscape. The heavier elements, like iron and nickel, sank to the center, forming the planet's core. This core would become the source of Earth's magnetic field, which protects the planet from harmful solar radiation. Lighter elements like silicon and oxygen rose to the surface, forming the Earth's crust. This crust, though initially unstable and frequently reshaped by volcanic activity, would eventually become the solid ground we stand on today. This process of differentiation was a crucial step in Earth's evolution, leading to the layered structure we see today. The formation of distinct layers, each with its own composition and properties, was essential for the development of a stable and dynamic planet capable of supporting life. The Hadean Aeon, named after the Greek underworld Hades, represents the earliest period in Earth's history, spanning from about 4.6 to 4 billion years ago. This era marks the very beginning of our planet's formation, a time when Earth was a chaotic and tumultuous place, far different from the world we know today. It was a time of intense heat, volcanic activity, and frequent meteorite impacts. The young Earth was bombarded by countless meteorites, some of which were large enough to cause significant changes to the planet's surface and atmosphere. The surface of the Earth was a molten sea of magma, constantly reshaped by volcanic eruptions and asteroid collisions. These collisions were so powerful that they could melt large portions of the Earth's crust, creating vast oceans of molten rock. During this period, the Earth's atmosphere was forming. The constant volcanic activity released a variety of gases from the planet's interior, which began to accumulate and form a primitive atmosphere. Volcanoes released gases from the planet's interior, creating a thick, toxic atmosphere composed mostly of nitrogen, carbon dioxide, and water vapor. This early atmosphere was vastly different from the one we breathe today, lacking the oxygen that is essential for most forms of life. There was little to no free oxygen, making the atmosphere inhospitable to life as we know it. The air was thick with volcanic gases, and the surface was bombarded by intense ultraviolet radiation from the young sun. One of the most significant events of the Hadean Eon was the formation of the Moon. This monumental event would shape the future of our planet in profound ways. The prevailing theory suggests that a Mars-sized object named Theia collided with the early Earth. This colossal impact was so powerful that it ejected a massive amount of debris into space. This debris eventually coalesced to form our Moon. The formation of the Moon was a critical event in Earth's history, as it had a lasting impact on the planet's development. The Moon's formation had a profound impact on Earth. Its presence influenced many aspects of the planet's environment and played a crucial role in stabilizing the conditions necessary for life to eventually develop. Its gravitational pull stabilized Earth's rotation, preventing extreme climate swings. Without the Moon, the Earth's axis might have wobbled more dramatically, leading to severe and unpredictable climate changes. The tides, caused by the Moon's gravitational pull, played a crucial role in the development of life in Earth's early oceans. These tidal movements helped to mix the ocean's waters, distributing nutrients and creating environments where early life forms could thrive. The Moon's influence on the tides also contributed to the gradual shaping of the Earth's coastlines, which would become important habitats for future life forms. The Archean Eon, spanning from 4 to 2.5 billion years ago, marked the emergence of life on Earth. The planet had cooled significantly since the Hadean, allowing for the formation of liquid water oceans. The atmosphere, while still lacking significant oxygen, was becoming less hostile. The first life forms were simple single-celled organisms known as prokaryotes. These organisms thrived in the harsh conditions of the early Earth, obtaining energy from chemical reactions rather than sunlight. Evidence of these early life forms can be found in ancient rock formations called stromatolites, layered structures formed by the growth of microbial mats. The emergence of photosynthesis was a pivotal event in the Archean Eon. Cyanobacteria, a type of photosynthetic bacteria, evolved the ability to harness sunlight to produce energy, releasing oxygen as a byproduct. This process gradually increased the amount of oxygen in the atmosphere, paving the way for the evolution of more complex life forms. The Archean Eon witnessed the formation of the first continents. Volcanic activity pushed land masses above the ocean surface, creating shallow seas and coastal environments. These environments provided new habitats for life to evolve and diversify. The Proterozoic Eon, spanning from 2.5 billion to 541 million years ago, was a time of dramatic change on Earth. This era, often referred to as the Age of Oxygen, saw the planet undergo transformations that would set the stage for the complex life forms we see today. One of the most significant events during this eon was the Great Oxidation Event. This monumental shift was triggered by the continued rise of photosynthetic organisms, particularly cyanobacteria. These tiny yet mighty organisms began to release more and more oxygen into the atmosphere through the process of photosynthesis. As cyanobacteria released more oxygen into the atmosphere, it reacted with dissolved iron in the oceans, forming iron oxide, or rust. This rust precipitated out of the water, settling on the ocean floor and forming vast deposits of iron ore. These deposits, known as banded iron formations, are some of the most significant sources of iron ore mined today. The increase in atmospheric oxygen had a profound impact on life. Oxygen, while essential for many modern organisms, was toxic to many anaerobic organisms that thrived in the low oxygen conditions of early Earth. This led to a mass extinction event, wiping out many of these anaerobic species. However, this extinction event paved the way for the evolution of aerobic organisms, which could use oxygen to produce energy more efficiently. This shift allowed for more complex life forms to develop, leading to the emergence of the first eukaryotic cells. These cells, which are more complex than prokaryotic cells and contain a nucleus, eventually gave rise to all plants, animals, and fungi. The Proterozoic Eon also witnessed the formation of the first eukaryotic cells. These cells marked a significant step in the evolution of life, as they allowed for greater complexity and specialization. Eukaryotic cells are the building blocks of all multicellular organisms, including humans. Another significant event of the Proterozoic eon was the series of snowball Earth events. During these periods, the planet experienced severe ice ages, where ice sheets extended to the equator, covering the Earth in a blanket of ice. The exact causes of these events are still debated among scientists, but they are believed to have been triggered by a combination of factors, including changes in the Earth's orbit and volcanic activity. These snowball Earth events had a profound impact on the evolution of life. The extreme conditions forced organisms to adapt or perish, leading to periods of intense diversification after each ice age. This diversification set the stage for the explosion of life forms that would follow in the subsequent eons. The Proterozoic eon was a time of both destruction and creation. While many life forms perished, the events of this eon laid the groundwork for the complex ecosystems that would eventually flourish on Earth. The rise of oxygen, the evolution of eukaryotic cells, and the challenges posed by the snowball Earth events all played a crucial role in shaping the trajectory of life on our planet. As we look back on this ancient chapter of Earth's history, we can see how the dramatic changes of the Proterozoic eon set the stage for the rich diversity of life we see today. The oxygenation of the atmosphere, the rise of complex cells, and the resilience of life in the face of extreme conditions all highlight the incredible adaptability and tenacity of life on Earth.